Okay, I think not every of you know me well, and so I would like to take this chance to make a self-introduction. My name is Zhigang Tian, but I typically go by Kevin, and you guys can call me Kevin. And I got my bachelor and master degree in China, and both in naval architecture and marine engineering. Then I went to the United States, did my PhD, and I defended last November, and came here in December the 4th, I think. And Professor Wu Yang Choi was one of my PhD advisors, and he invited me to come here to work with him, to continue some part of my PhD study. So here I am, and that's my contact information. Over there, feel free to give me a call or send me an email if you have any questions. So in the final 4 lectures of this engineering mechanics in ocean systems, I will talk about environmental laws on ocean systems. And the objective is just to give you a brief introduction of sea environments and their laws on ocean systems. So there are 4 references. I would like you take notes or write it down. And because the first one is Sea Laws on Ships and Offshore Structures is considered to be one of the most classic books in this area. And it's more engineering toward it. It's more like doing practical things. And the second one, Marine Hydrodynamics, is also written by this famous guy. I think you all heard about his name. And this book has some applications, but it's more mathematical oriented. So you have to have a strong mathematical background to read through the book. And the third one, Water Wheel Mechanics for Engineers and Science. This actually was the first water wheel books that my advisor recommended to me to read, so I recommended to Yukwan Hong to read too. So this one is a good start book, and the last one is very mathematical. So whatever. So I would like to introduce a few keywords for my lecture. Keywords that I would like to cover, all of this. The first one is sea environment. And second one is marine structures. And third one, as you know, the famous dimensional analysis. And at this stage of this lecture, I think you all have a good idea about water wheel theory. So we're going to review a little bit on the linear wave theory. And I'll introduce random phase and random amplitude method to simulate the sea environment. It's called random phase amplitude method. So it would be beneficial to all of you to know a few short-term statistics and long-term statistics of the ocean waves. So long-term and short-term statistics of ocean waves. And then we'll start with the three typical methods we use to compute wave loads. The Morrison equation, and F key, that's fluid Krylov force, and then it's the diffraction theory. And since wave breaking and wave impact on the offshore structures and ships is a very complicated problem and sort of very important, so I would like to, if time permits, do a little wave impact thing. Wave impact and groundwater load. So this is for the wave part. So we're gonna have current and wind loads on offshore structures. So I'll go through the basics and then talk about the flow separation and VIV. So we have current, wind, and flow separation. Oh, so it's blocked a little bit right here. Flow separation, I assume you have so wind, current, flow separation, and VIV, that's vortex-induced vibration. That's pretty much what I'm trying to cover, and how far I can go, I don't know. So let's see. And if you have any questions, stop me. Don't feel just feel comfortable to stop me anytime. Okay. First thing is introduction. Always introduction. Introduction is kind of important, I think. Whenever people make introductions and let people know about you, and it's a good thing. So we do lectures, we do introduction too. Ocean engineering is a very unique and complicated discipline. In the sea environment, we know the water is a high pressure medium. Nowadays, the offshore engineering try to go deep sea for like 10,000 feet. That's 3,000 meters, right? 3 kilometers downgrade. So even you do the statics, you can see the pressure rho g h, and it's very high pressure. And sea environment, seawater is very corrosive. You put a steel or aluminum in there, you're gonna see the corrosion. And it has waves, current, and wind, so that gives more trouble when we try to design structure to like doing offshore drilling or get oil. And when the propellers or high-speed vehicles moving on the surface, those high-speed can usually introduce cavity. Those cavity is very damage the propeller, the ships fairly easily because of the pressure, and you probably see examples. Oh, we got students there too. Okay. Say hi. Sorry, I didn't notice you guys. Okay. Now I have some. I look at you from time to time. Okay. And marine hydrodynamic problem spans a broad range of scales. From the micro scale when we do welding to get the structure members together, and to the full scale of the structures. So the scale is always a problem. So as for the marine structures itself, and is considered to be one of the largest, the largest human being-made systems. This picture you probably seen from somewhere. This is this is a spar, I think. And if we move the spar from the sea, put it on top of this city, which I think is Houston. You can see the size of this spar. Considering the mooring lines, it's typically like less than a meter of diameter for like 3,000 meters. It's fairly long, and the mooring lines and the risers in the middle. Here, this is for oil, and on the top you have a processing module. So it's a very complicated problem. So when we design this structure, we have to consider a lot of things like wave loads, wind loads, current loads. We have to make sure it's stable on the surface. It's not going to capsize. And speaking capsize, you guys might know a few days ago there's an explosion in Gulf of Mexico, and sank a drilling rig. It's called Horizon, Deep Water Horizon, operated by BP. It's owned by Transocean. That rig was built in 2001, and it cost like $350 million. Then now it's probably doubled. It's almost $1 billion offshore, drilling rig, and it sank. So what a cost! So we have to consider every detail of things in the design, in the operation. So this is all related to, and I provide to see ocean system engineering. So let's look at what kind of sources do we have in the ocean. Obviously, we have surface waves, right? We have current. We have wind. So what else? So any of you can figure out anything else? The loads that can be an excitement to the structures. Okay, I'll list a few. Ice. Why ice? Nowadays, we found that in the North Arctic, there's a tremendous amount of reserve of the oil, carbon hydro related energy stuff. So we want to do some business in that area. So unfortunately, it's covered most of the time by the ice. So tsunami. So I think you all heard that. Earthquake. Come on, earthquake. So I forgot how to write this word. It's my bad. And volcano eruption. You all know the Iceland thing. But too bad that cost the airline companies more than €1 billion. It's not to us, but it's still a bad thing. So most of the time, the sea environment is a combination of all of this or some of this. So in this lecture, we will focus on these three topics, and this one is the main part. So let's see some typical problems of seakeeping and wave loading for ships. Here the first one, this is a helicopter trying to land on this ship. If the ship motion is too large, the relative motion, that's not good. Also this container, this ship, it has containers. If the acceleration is too large, the container can easily, collapse and, lost or get damaged. And this is the relative motion of the bow bottom to the slamming, to the water. It's called slamming. It's a high pressure, very instantaneous process, very quick, and the resulting pressure can damage the ship fairly easily. And this is green water load. And this is the very dangerous case of beam sea. You guys heard beam sea? Beam sea. Beam. So this is a shape. The waves comes from here. Is head sea comes from the side. Beam sea. This is the one of the most dangerous situation for the ship. So whenever you maneuver ships, you don't want to do this. You want to toward the waves. And also there's a following case. And sloshing, obviously you know. And then this is the hogging and sagging situation. Hogging and sagging. So this is the introduction, so some basic conceptions. This is the shape. So I'm a bad drawer, but anyway, this is the wave. When the length of this shape is, approximately equal to the wavelength, so in this situation, this part is like suspended from the water, so it has a very large momentum. You should getting the ship bending like this way because it has. This is due to gravity, and this is due to the floating force, buoyancy, and it will introduce a very large momentum in the middle section. This is called hogging. Hogging, yeah, I think so. And then the other case is opposite. Let me use. This is the good thing. Why we? So this is a crest. It goes. The force goes from the middle, and then due to gravity, it's dropping. This is sagging. Hogging and sagging. And sagging. Okay. So for the offshore structures, when you do a drilling on the bottom, you don't want the drilling platform motion, make large motions, especially the heel motion. And so now we're having a mobile harbor project. We try to load and unload the containers. So you don't want the relative motion and acceleration of these platforms is too much. It's the operation, is not safe. and also the braking strength and flexibility of the rider systems. Those are the typical problems in ocean engineering. And if we recall the equation of motion, for safekeeping problems, we have m plus ma double dot plus, what do I have? B structure x dot. So why do I write this large? I'm limited to this space. But anyway, K hydro plus K structure for the safekeeping problem. This is structural mass and this is added mass. I assume you have go through this in the previous lectures, right? And this is acceleration. This is damping due to hydrodynamics, damping due to structures, and those the hydrostatic restoring force and the structural stiffness. And this is the external loading, which we're gonna try to figure out in the next 4 lectures, due to waves, currents, or winds. So this is a very complicated process. You probably know. Actually, in the safekeeping problem, the main things is you figure out those coefficients. Once those coefficients is done, you can easily write a program to solve this numerically. And this is typically a 6x6 matrix. We can do theoretical analysis to figure out the sum of this part, but the scope of application of theoretical analysis is very limited because it's too complicated. But theoretical analysis is very important. You have to know the physics. You have to have a very solid background before you can do anything, before you can do the numerics, before you can do the experiments. So theoretical analysis is necessary, although in real application it's not obvious that it has many applications in practice, but everything is built on that. So we can solve these things with numeric simulations. It's very important, but nowadays, whenever you present some numerical results, people always ask, do you have experimental results to compare? So if you say no, they would not pay much attention to your calculation. Why is that? Essentially, numerical simulations can give you any results if you manipulate the coefficients. You tweaking, I'm not saying cheating, but you based on your experience, you do adjusting the coefficients. So whether a code is robust or not based on blind test, I don't know the experimental results. I do a blind test. I do my computation. And then I compare to my measurements. If it match, means good. If it doesn't, means you have something tweaking work to do. But if you tweak your code based on the experimental results, or it works for this specific case, will it work for another case? Or any other cases? How confident are you in your code? So people tend to trust more on the model tests, experimental results, than the numericals. But I'm not saying numericals is not important. Numericals is very important, especially nowadays. as the development of computers and the high technologies, some people even can simulate the full model testing process numerically. So that saves a lot of money, a lot of time, and you can do, virtually as many as trials as you wish. So that's good. But what I'm trying to say, model test is one of the most robust and reliable ways to validate or examine your theoretical analysis, your numerical simulations. So speaking of model test, we can do full-scale tests, right? But it seems if you do a full-scale test, that's gonna take you much time, cost you too much money. So as I mentioned, building a full-scale rig costs about $1 billion. So nobody wants to do that. So we have to do a model test with a smaller scale, and therefore we have a scaling issue. So how do we scale model test results to the full scale results? So that's more or less what we so-called dimensional analysis. So a traditional way to do dimensional analysis is we identify the three basic or fundamental skills: mass, length, time. So we identify parameters that is a function of a combination of these three, and remain the parameter we want to know as the unknown, and write, based on our experience or knowledge, we can state the final scaling law. Here's a little example that I liked the most. That's from one of my advanced fluid mechanics classes, not in the ocean engineering area. So that is prove the Pythagorean theorem with dimensional analysis. Prove the Pythagorean theorem. So you guys probably know a lot of ways to prove this, how to do this, right? A, B, C, A squares plus B squares equals to C squares. How are we going to do this? So the known is this angle, alpha, and the area of this triangle and the length of this long side, C, A, and B. So we're going to prove this using dimensional analysis. Okay, the first thing is we identify M, L, T. So knowns, the area, the length of the side, and then the angle. There's no mass involved, right? No time involved, right? This is good. And for area is length squared, and this is length. And this angle is essentially radian. Radian is nothing, right? Radian is, length over length is nothing. So now we're gonna write a scaling law. We have two parameters can only give us one. Is that correct? Area, if we, this is a dimensionless parameter, A over C squared is a function of angle. So that's the only way we can identify a law. So what are we gonna do next? We make a line, a virtual line perpendicular to this this side of the triangle. So this angle is alpha, right? In this one, if we assume this is area is A1, this is A2, we do similar scalings. We have A1 over A squared. Same, because this is alpha, same function. And we have A2 over B squared, right? A1 plus A2 equals A, right? So this is the same. C squares equals A squares plus B squares. This is a very intriguing example. So I like it very much. So back to our analysis in ocean engineering. I used about 30 minutes. Oh, 40 minutes. 30 minutes. Okay. So I'm on time. Good. So ocean engineering. So this is not a strict dimensional analysis, but our purpose is to trying to figure out the relative importance of three basic forces. What are the three basic forces? Inertial force, gravitational, force, and viscous force. So the balance of these three forces is considered as a very important thing to our in new architecture. So what considering shape, the basic known parameters we have would be the length, right, of the shape, velocity, fluid density, acceleration, and the dynamic viscosity, which is mu. In Greek is mu. So it's mu. Okay. So how do we find the inertial force? Inertial force is like this: U rho U squared L squared. I'll finish writing this first, and then I'll explain how we get this. Mu U L. Okay. What is inertial force? Put it in a simple way, but may not strictly correct. It's FMA, right? F equals MA. F equals to M A, which is the acceleration, which is du dt, right? U is the velocity. What is m? Rho L, right? U is U. What is t? We don't have a t, but we do have a LOU. LOU is t, right? Scale, dimensional per dimensional, say. So this gives rho L squared U squared. This is how come we have an inertial force. Gravitational force, this is, right? Rho L, this is straightforward, obvious. This is the volume times the density and times gravitational acceleration. What is viscous force? So any of you remember this thing? Stress du dx times dynamic viscosity. This is one of the constitution laws you have in your basics, right? I think you had that. So this one is here, U is here, L. So we have U over L, right? This is stress is force per area. So if we are talking force, we need an area, right? Area squared. So that's why we have this one, right? This one goes here. So at the beginning of my study here in the ocean engineering, I always had problems to memorize those forms. Then I decided not to memorize them. Try to figure out how they come. So this is the way they come. So hopefully you can, even you forget those forms, you can do your own analysis and figure out. Okay, so this is the three principal fundamental forces in ocean engineering. With these three skills, we can know the relative changes among these three forces. For example, we have a 100-meter ship, and then we have another one. They travel at the same speed. From here to here, the inertial force will increase by 4 times, right? This gravitational force 8 times, and this viscous force is 1 times. This change in the magnitude of these three forces will change the balance between the three forces, because this one increased more than the others. So the fundamental theory or the fundamental analysis we use to solve this problem might change from one to another. Okay. And the second important thing is we do scaling. If the three forces work on the shape, act on the shape simultaneously, and they preserve the relative magnitude to each other, we achieved a dynamical similarity, which means the balance in this scenario, if relative magnitude between the three forces keep unchanged in another system. So we see these two systems is dynamically similar. This is very important to us do a model test. That's the only way we can scale from one test to another, whatever the full scale test or another model test with different scales. So now let's look at the relative magnitude between the three forces. We have inertial force over gravitational, which is, you plug in those forms like inertia rho g, right? You end up with u squared g over gl, right? So this is one important, this is called fluid number. But in definition, people use the square root of this thing. It doesn't matter, it's just a definition. This is the fluid number. It's very important. It means inertial force over gravitational force. It gives you the relative importance of the two forces. And then the next one is inertia over viscous. This one is rho ul squared over ul. This equals to rho ul over nu. This is the Reynolds number. It represents the relative importance between the inertial force and viscous force. So in reality, we do not use dynamic viscosity, we use kinematic viscosity, which is nu, ul over nu. So you can see nu is equals to mu over rho, right? So you move this to the denominator. Okay, so that means if we keep both fluid number and the Reynolds number the same in our test, we're going to achieve dynamic similarity. Then we can scale from one result, model test result, to the full test results. But there are a few things we need to address. This is my favorite part because it took me a while to figure this out, and maybe my teachers told me before, but I didn't pay attention in the class, so it takes me some time. Okay, the first thing I want to say for this dimensional analysis is Reynolds number ul over nu. This thing for water is on the order of 10 to the minus 6. So typically, Reynolds number will be large, which means what? Inertial force is more important than the viscous force. So that's the reason we can use diffraction theory or other things to compute the wave loads without considering the viscous. And that's the reason we can make assumption that it's inviscid, the fluid. But this is in general true. But if you are considering the boundary, the boundary layer problems, also the large ships with large frictional contact with the water, so you have to take that into account. But this is in general. This is something we noticed from the dimensional analysis. Okay, we have Reynolds number, we have fluid number, which is U over square root of GL. We want to achieve dynamic similarity. We want to keep both of them, both increase twice, 3 times, or 5 times. Which means if we want to achieve dynamic similarity, the ratio has to be a constant. Is that true? Let's see. The ratio of this thing equals to G to the half L to the 3/2 and over nu. We know this thing is not changing, right? This gravitational acceleration, if it's changed, we're going to have trouble. And the length can change. Viscosity for water, it's probably not. So we have a non-constant here. So we have no way to achieve this condition for test in water, in reality test. Of course, you can do test in like mercury, which has a much larger, kinematic viscosity. But in general, this is not achievable. So we are screwed, right? We cannot achieve dynamic similarity. Now let's take back up a little bit. Assume, okay, let's pretend we can do the dynamic similarity. Let's pretend this is achievable. So let's look at this number, Reynolds number. If we have a full scale ship moving at 20 knots per hour, that's 20 knots. That's equals to 10 meters per second, right? And the length of the ship, reasonable assumption, 100 meters. For our model scale, 2 meters. Is that alright? 1 to the 50 scale is reasonable. You figure out how large this U is. (500 meters per second). In the model test, can we do this? 500 meters per second? Because we are keeping this is constant. This one, UL nu, this is full model equals to UL nu over test. So this one is the same. So this one is 10, 100, and this, no. This is 2, so this is 500, right? Okay. Even we can achieve the dynamic similarity, it's not practical, it's not feasible to do a test, model test, a towing tank 500 meters per second. It's like a rocket, right? Going to the air. So we're so screwed until this big guy comes out. Fluid's hypothesis. What does it say? Okay, if we're doing ship resistance, you can separate the resistance into 2 parts. One is frictional. One is residual. Whatever. One is depend on fluid number. The other is depend on Reynolds number. And he's assuming that the Reynolds number Oh, I should write the other way. This one is for the. Sorry, let me. This is Reynolds number, and he's assuming that the frictional component is related to Reynolds number, which can be done with a standard procedure. We use dragging a plate, under the water, so we can figure out the drag coefficient. Let's call it C of R. And the other is residual. We can have a coefficient. Let's call it this. Okay. So when we do experiments, we match the fluid number. So the standard procedure would be okay. We do a towing test. We figure out the total stress, total frictional, total resistance. We call it in terms of a coefficient, C of T. Well, you can easily figure out it would be a force over rho U squared or L squared or something. It's something like this. Yes, this is we're saying everything is like this. Okay, I'm matching the fluid number, so it will give me a Did I do the right thing? Yes, it will give me this thing. This is for model test. Then reality, when we do skills, well, this one is measured, this one is measured, this one we can, figure it out like this. So in reality, we know this one. And key? No. So I'm still having trouble with this thing. But anyway, so we model test, we measure the total coefficient. Let's see this one. And we have this Reynolds number, and we can, based on the recommendations of ITTC or whatever, we can figure out this one. And then, based on this, we can have fluid number computed, right? And then we scale this one in full scale. We have CF. And then based on the Reynolds number of the real scale, we can figure out this coefficient. And then the total would be this one plus CFR, right? This is the way we do the ship resistance. So the important thing here is you need to understand in model test we match the fluid number, this one, and you also need to know it's not practical to achieve dynamic similarity directly. Okay, enough. So now let's move on to the first thing, ocean waves. Okay, based on the restoring force, we can make a crude classification of the ocean waves. We have sound, capillary waves, wind waves, and swell, tsunami, internal waves, storm surge tides, and planetary waves. And the typical wave period is listed here, and the physical mechanism is here. So, for example, capillary waves is typically 5 to 10 centimeters, or no, 5 centimeters. So you can see that at the beginning of when wind blowing on the water surface, those small waves is called capillary waves. It's maintained by the surface tension. And for the general waves, we see like from a meter to like 20, 30 meter is physical mechanism is gravity. And also this part is on the air-water interface, is on the surface, sea surface, and we're gonna focus on these wind waves. There are some other things, and if you are interested, you can Google it, and then so now let's review the linear wave theory. Review of linear wave theory. So how many of you are confident and say, okay, I have enough knowledge about this part? Okay, so what I'm going to do is just list the how much time do I have? 1:40, half an hour. Okay. List the governing equations, the boundary conditions, and the solution. And for whenever we do something, we're gonna have to have a clear definition notation and definition of the coordinate system. So it's like this, and there are a few assumptions we make before we can proceed, like homogeneous, irrotational, incompressible, inviscid. And since we are talking the wind waves is small scale, the Coriolis force, which is due to the Earth's rotational, we can ignore it. Otherwise, we're gonna have a totally different governing equation, and then we assume there's no current, so there's no wave blocking due to the current, and we ignore the surface tension, which is essentially important to the capillary waves, and we assume the water depth is constant, so there's no diffraction due to the change of the bottom the water depth, and we also assume the atmosphere pressure is constant, and we also assume it's small amplitude waves, which means low stiffness. So we are engineers, we do things based on assumptions, but I wanna ask you to remember, whenever you do assumptions, you keep that in mind. If you later on you do analysis, you find some conflicts or something, that means one of your assumptions is not proper. You're gonna go back and redo the assumptions. That's always important. Okay, now if we in an ideal fluid, we have U. We define a velocity potential is like this, and we have from the continuity equation we have a Laplacian equation, right? And this is the governing equation and boundary conditions. we have a seabed. We assume, I gotta use W. We assume there's no water goes into the seabed, so this one is 0. On the free surface kinematic boundary condition, so this I'll just write it down, and this is at z equals to minus d. Based on that notation, this is z approximately to 0, and this pressure is 0. This is the dynamic condition, boundary condition. Okay, that's it. So from here we can do some further work based on the Bernoulli's equation. Okay. We can have this one. Probably you're more familiar with this one instead rather than this one. Okay, from all of these things, we use separation of variables. We use the boundary conditions. We can solve this thing analytically. So we end up with the analytical form for this sinusoidal wave h over 2 g omega cosine z plus d cosine omega kx minus omega t, and also the surface is h over 2 I think it's cosine, so it's 90 degrees out of phase. And also one important thing I want to say is the dispersion relation. Oh, sorry. Okay, let me change it. This one better? Oh, I'm sorry. So can you see it clear now? It's terrible. So that's a good example to stop me. Thanks. So here, this one's clear. Do I need to rewrite it? Ah. What is called? That is called trying to think out the word. Well, I don't have enough time to make jokes or other things. Okay. That's creative thinking or diverse thinking. So when he told me it's not clear enough, I choose to change the pen instead of turning on the light. So one of the students turned on the light. That makes it better. So this is called, I think it's called diverse thinking or something. Anyway, good. So we have this dispersion relation. So the waves is dispersive. What does dispersive mean? That means the velocity of the wave is a function of wave number or wave frequency or wave number. That's so for deep water, this one goes to 1, right? For shallow water, this one goes to KD, deep water. For shallow water, this one goes to KD, so kg squared GD. Is this dispersive waves? No, this is not, because it's propagating speed is not a function of these two. So, okay. And then we can do similar things to find the velocity, right? Since we have the potential. Velocity U and V, which is, as complicated as my writing, which I'm not going to show here, but I do want to show you one figure. This is the water particle trajectories in linear waves. This is for shallow water. This is the criteria we separate what is to determine whether it's deep water or shallow water. This is intermediate and this is deep water. This is from one of the references. For shallow water, you notice that as we go deep from the surface, the vertical velocity dies away, but the horizontal velocity does not change. And so that's the important. In shallow water, close to coastal, we have transportation of the sediments, right? That's actually one of the important topic for the coastal guys. The coastline. For this one, so both vertical and horizontal velocity dies away. So essentially, we have no velocity here. Okay, now, so we move on to the ocean waves. Ocean wave is a random process. A random process, what is a random process? If without giving information in the sea surface, you pick up one point, you don't know the surface height. You probably know the probability, like at 50% of, out of 100 peak, you probably have like 5 meters or 2 meters surface height. But you cannot predict specifically how high it is without giving extra information. So if we define, let's write this down, probability description of general random process. Okay, if we define this thing, this is a random variable, so equals to a surface elevation at a given location and at a given time. So consider this larger area, a top view. So we see the sea from the air, and there are many waves here. At a given time, that's a snapshot of the surface waves. You pick one point here, it's a value. Pick one another, is another value. You cannot make a direct connection between the two because it's random. So this is the random value we defined here at any point. So now we see cumulative probability density function. What does that mean? That means it is a function of x. In that view, I pick a point, and the value of this point is less than this given value. How large is the chance that is less than this value? It's called cumulative probability. And then another definition is the probability density function. That means I pick a point as that thing is equals to given the value. You see the difference? This is cumulative. That's the probability for all values that is less than this one. And this one is equals to the probability that equals to this one. Why we are looking at? Because later on you'll find the surface elevation in the sea follows a normal distribution, while this amplitude or wave height follows a Rayleigh distribution. We need that information to do a few things. So how many of you have had probability or statistic class in when you were undergraduate, or right now you having any? Did you guys have any experience with these things? No? Yes? Okay. So that is a no. I take it that way. Okay. So a few other definitions, which is the mean or mathematical expectations. So assume we have n samples, so that's just the mean, right? We have variance. That's I'll write it in squared. This what is a good symbol for new? Okay, this is autocorrelation. Okay. Autocorrelation. So I hate this part because it doesn't have much explanations. It's just a formula, so you have to write it down. There's no other way to explain. This is why I call the definition. So we have two random process, one and two random variables, and we know the joint probability of this thing, these two things. We call it and then the autocorrelation is defined as the integration of Okay. So this is. So I feel responsible to let you know the definition, but we might not use these things later on. Okay, then let's see for time. The next concept would be stationary random process. A random process is stationary if stationary random process. So a random process is stationary if its probability distribution are invariant, means unchanged, under a shift of the time scale. What does that mean? I have two snapshots C to C from the top. This is 1, this is 2. So I have many measurements here. I do static analysis. I have the mean, I have the variance, I have the correlation or whatever it is. This is T1 at one time. At a later time, I have other measurements. I still can do these things. Those are the same. This is called a stationary random process, because this is itself is a random process, but it's not from here to here. The time scale does not matter. It means a stationary random process. The next concept would be ergodic process. What does this mean? This means it is a process. So this one means a process is ergodic if is ensemble statistics equal to is temporal statistics. I have random variables here at T1. I can have certain process, statistical variables, and also the PDF, the probability density function, and also the CPDF cumulative things. Now, I put a measurement device here and follow through. I take many measurements. At the end, this is T2. Now this measurement signal is like this, right? Still like waves. And here is still like waves. If I do statistical analysis in this space, this is spatial information at one time slot, and do statistic analysis to this temporal signal, this one gives another set of this thing. If the two are the same, it's called ergodic. Why I'm put too much, so much time on this? In reality, when we do measurements, if we use a camera, how large a range can we cover? 10 meters, 10 by 10? That's a very small area. Consider how large the operational area of the sea is very large. So it's not practical to figure out the statistics of the waves. Instead, we put a probe here. We can measure 1D or 2D signals to do things. And we use this signal to figure out all those informations. And the number one assumption is this assumption, that the ensemble average statistics in space is the same in temporal. How good is this assumption is? So reality is like if in a storm case, 2-3 hours of measurements should be okay. And most you can do 10 hours. That's, based on the experience, and it's work done by mostly oceanographers or to the observationary guys. Okay, now we assume that we can use this measurement to represent the measurement in space. We do analysis to spatial temporal signals, which is measured. This is t equal to 0. Goes to, we have waves like this, right? This is not one single frequency wave. It has many components inside. Each component has a amplitude. Maybe we can see this is based on linear superposition. Okay, we can see this is the assumption of omega 1, omega 2. Those are sinusoidal waves, and also others, right? Even higher, So how many Fourier analysis or FFT? That means, okay, any signal I can decompose it into these sinusoidal waves. There's a rigorous provement of this thing. Okay, now if we measure the amplitude A1, A2, A3, and we plot it. So this is omega 1, omega 2, and omega 3, like this. This is called a wave spectra. It's actually called a amplitude spectra. In reality, this is A. In reality, we want to check the energy. So that's the energy spectra. In reality, it's all in the sea. If we do enough measurements, we can find those nice curves here. It's quite often a function of the wind speed, direction of the wind, Also the wave fetch, I mean, that means how far the wind blows and how far the wave is, how far your measurement is. In developing phase, those are the two examples for the wave spectra you see in the developing phase and decaying phase. So at the beginning, there's no wave, and wind starts blowing, and we have those small waves, capillary waves. That means high frequency. This is frequency. And later on, the waves grow, becomes like this lower energy, lower frequency. And that's the reason you see the peak from high frequency to low frequency, the transfer. Also, the energy is increasing, so it goes this way. When it's decay, you see this one. There's no from this point on. There's no one input. It will decay. It slowly becomes calm water. That's you see the energy from high frequency to low frequency. If you draw a line of the peak, here is obviously peak is here, and this peak is here, and energy decreases. That's how it looks like in reality. And based on measurements, there are a few well-known spectras, like the PM spectra. That's based on the measurements. Pearson was called Pearson. So, how many minutes do I have? 5 minutes? So this is just an example. This is a wind velocity. So you can see it's a function of with alpha equals to 0.0081. This is based on measurements. You don't have to memorize it. It just show you something. There are other spectras like the John Swap, ITTC, a lot of things. Okay, I think I should stop here. Although I got quite a few things to cover I planned. But anyway, we can do it next time. And as I mentioned, after this, I'll introduce to you a few methods to simulate the random waves in ocean, and then we're gonna move on to how to compute wave loads, and at the end I'm gonna try to cover a few topics on the current and wind. Okay, that's it.